Carbon-neutral fuel made from sunlight and air. Researchers from ETH Zurich have developed a novel technology that produces liquid hydrocarbon fuels exclusively from sunlight and air. For the first time worldwide, they demonstrate the entire thermochemical process chain under real field conditions. The new solar mini-refinery is located on the roof of ETH's machine laboratory building in Zurich. Carbon-neutral fuels are crucial for making aviation and maritime transport sustainable. ETH researchers have developed a solar plant to produce synthetic liquid fuels that release as much CO2 during their combustion as previously extracted from the air for their production. CO2 and water are extracted directly from ambient air and split using solar energy. This process yields syngas, a mixture of hydrogen and carbon monoxide, which is subsequently processed into kerosene, methanol or other hydrocarbons. These drop-in fuels are ready for use in the existing global transport infrastructure. Aldo Steinfeld, professor of renewable energy carriers at ETH Zurich, and his research group developed the technology. This plant proves that carbon-neutral hydrocarbon fuels can be made from sunlight and air under real field conditions, he explained. The thermochemical process utilizes the entire solar spectrum and proceeds at high temperatures, enabling fast reactions and high efficiency. The research plant at the heart of Zurich advances ETH's research towards sustainable fuels. A small demonstration unit with big potential. The solar mini-refinery on the roof of ETH Zurich proves that the technology is feasible, even under the climate conditions prevalent in Zurich. It produces around 1 deciliter of fuel per day. Steinfeld and his group are already working on a large-scale test of their solar reactor in a solar tower near Madrid, which is carried out within the scope of the EU project Sun to Liquid. The solar tower plant is presented to the public in Madrid at the same time today as the mini-refinery in Zurich. The next project goal is to scale the technology for industrial implementation and make it economically competitive. A solar plant spanning an area of 1 square kilometer could produce 20,000 liters of kerosene a day, said Philip Furler, director, CTO, of Synhelion and a former doctoral student in Steinfeld's group. Theoretically, a plant the size of Switzerland, or a third of the Californian Mojave Desert, could cover the kerosene needs of the entire aviation industry. Our goal for the future is to efficiently produce sustainable fuels with our technology and thereby mitigate global CO2 emissions. Two spin-offs already emerged from Aldo Steinfeld's research group, Synhelion, founded in 2016, commercializes the solar fuel production technology. Climeworks, founded already in 2010, commercializes the technology for CO2 capture from air. Box how the new solar mini-refinery works. The process chain of the new system combines 3 thermochemical conversion processes. Firstly, the extraction of CO2 and water from the air. Secondly, the solar thermochemical splitting of CO2 and water. Thirdly, their subsequent liquefaction into hydrocarbons. CO2 and water are extracted directly from ambient air via an adsorption-desorption process. Both are then fed into the solar reactor at the focus of a parabolic reflector. Solar radiation is concentrated by a factor of 3,000, generating process heat at a temperature of 1,500 degrees Celsius inside the solar reactor. At the heart of the solar reactor is a ceramic structure made of cerium oxide, which enables a 2-step reaction, the redox cycle, to split water and CO2 into syngas. This mixture of hydrogen and carbon monoxide can then be processed into liquid hydrocarbon fuels through conventional methanol or Fischer-Tropsch synthesis. Hawk's pursuit of prey has implications for capturing rogue drones. Previous research has shown that falcons intercept prey using the same guidance law as homing missiles, called proportional navigation. This guidance law is optimal against smoothly maneuvering aerial targets, but is prone to being thrown off by the zigzagging maneuvers of terrestrial prey like hares or jackrabbits, and will not necessarily lead to a feasible flight path through the cluttered habitats that hawks frequent. University of Oxford researchers, Dr. Caroline Brighton and Professor Graham Taylor, used high-speed cameras to capture the flight trajectories of 5 captive-bred Harris's hawks during 50 flights against an erratically maneuvering artificial target. Dr. Brighton said, "We filmed our hawks flying after a dummy bunny, which was an artificial target that we towed at speed around a series of pulleys laid out to produce an unpredictable course. Using video reconstruction techniques to measure the 3D trajectory of the hawk and its target, we then ran a computer simulation to see how closely the hawk's attack behavior was modeled by different kinds of guidance law. The researchers found that Harris's hawks use a mixed guidance law, in which their turn rate is determined by feeding back information on the angle between the direction to their target and their current flight direction, together with information on the rate at which the direction to their target is changing. The researchers argue that this mixed guidance law reduces the risk of overshoot in the close pursuits to which hawks are adapted, but would produce an inefficient flight path if used in the long-range interception behaviors of falcons. The findings have applications to the design of drones for pursuing and capturing rogue drones in cluttered environments. Professor Taylor said, "Last year's Gatwick incident showed just how far we are from being able to remove rogue drones quickly and safely from a large open space, let alone the cluttered airspace of an urban environment." Hawks are masters of close pursuit through clutter, so we think they have a thing or two to teach us about how to design a new kind of drone that can safely chase down another.